Okay, and the masked professor is on the air again. All right. Well, good afternoon, class, he says to an empty room. All right, so last time here in computer-aided manufacturing, we were talking about control systems to do with automated manufacturing. So we will pick up here with steady state optimization. In this case, we are talking about optimization techniques in which the process has these characteristics. We have a well-defined index of performance. We have a known relationship between the process variables and the index of performance. The system parameter values optimize index of performance and can be determined mathematically. So it's an open loop type system, and our optimization techniques may include differential calculus and mathematical programming. In this case, we have our input parameters into our process, output variables that add up to a performance measure. Our controller does not measure the output variables. It adjusts the input variables, input parameters, excuse me. We have a well-known index of performance, as I stated a moment ago. We have a mathematical model of the process and our index of performance. And we use an algorithm to determine the optimal parameter values. Now we have steady state optimization. It's open loop. If there is a problem, it cannot compensate for any type of disturbance. So our adaptive control is a self-correcting form of optimal control that includes feedback control. So in that case, we're measuring the relevant process variables during operation, right? That's our feedback control. We use a control algorithm that attempts to optimize some index of performance for our optimal control. And what luck, a student has just arrived. All right, so our adaptive control operates in a time-varying environment. The environment changes over time, and those changes potentially have an effect on the system performance. So, the example they give us, a supersonic aircraft will operate differently in subsonic flight than it does in supersonic flight. If the control algorithm is fixed, the system may perform quite differently in one environment than another. So an adaptive control system compensates for that changing environment by altering aspects of its control algorithm to achieve the optimal performance. What could be clearer than that? All right, so in adaptive control, we have three different functions. We have an identification function. So our current index of performance is determined based on the measurements of the process variables. We have a decision function that can decide what changes should be made to improve the system performance. That may be a change of one or more input parameters, or it may alter an internal function of the controller. And a modification function that implements the decision function. So in that case, we are concerned with what is changing in the hardware aspect rather than the software aspect. Okay, everything okay there?
Mm-hmm.
All right, you only missed a few minutes, so you'll be able to go look at the video later. So our adaptive control system, we have our input parameters, we have our output parameters, and our performance measure. The process here in the middle, there are measurements of the, can I help you, ma'am? You seem to be looking for something.
Yeah. One of the students, I think it's an engineering program, he borrowed a vacuum pump from us in the chemistry department.
He borrowed the vacuum hose?
The pump, vacuum pump. And I
Okay.
don't know if I'm in the right building, or, I don't know if you even know him, Jonathan?
Jonathan. Well, we have some Jonathans.
Might be electrical engineering, I think Jonathan. Wait, which Jonathan? Do you know his last name?
Jonathan Shanina, maybe?
Shanina?
Yeah, he has a weird name, weird last name.
Might be on that side.
He might be working over in the electrical engineering mod, or it might be over in the fabrication lab.
No, definitely not. Probably not the lab.
Okay, I would try the electrical engineering mod on Marcy's suggestion first.
I thought he was in there, the last time I had class, he was next door.
Okay, well, maybe he's next door. Apparently I'm just very confused.
Yeah, I'm not sure where he does his little research at. His little plastic octopus hand, little research.
I
that he
know
goes doing.
sometimes he was working in the chemical engineering room, which is 312.
Okay. So it's either this building or probably the EE building. Next.
Yeah, I thought it would be in here. But, it's like, there's always classrooms in here.
You could also check next door.
All right, let me check next door.
Okay, well, all right, so our measured output on the variables, our index of performance, are both going into our identification. Our algorithm is making a decision, and a modification in the hardware is being made that adjusts the input parameters in the adaptive control system. All right. So when we start talking about online search strategies, in this case it's an adaptive control in which our decision function is not defined all the way. So the relationship between input parameters and our index of performance isn't known, or not, at least not well enough to implement the previous form of adaptive control. So in this case, experiments are used on the process And small systematic changes are made on the input parameters, and we observe the effects from that. Based on those observed effects, larger changes are made to drive the system towards optimal performance. So we can think of it as machine trial and error. All right, so when we talk about discrete control systems, in that case, our process parameters and our variables are discrete. And that those process parameters and variables change at discrete moments in time. Those changes are defined by the program of instructions in advance. So there are two reasons that those changes might be executed. One, the state of the system has changed, so that's an event-driven change. Or a certain amount of time has elapsed, and that's a time-driven change. Event-driven changes are executed by the controller in response to an event that alters the state of the system. So an example, a robot loads a part into a fixture, and the part is sensed there because there's a limit switch built into the fixture. Another example, a diminishing level of plastic in the hopper of an injection molding machine triggers a low-level switch, and that opens a valve to start the flow of more plastic into the hopper. Another way might be that we have a way of counting parts that move along a conveyor past an optical sensor. Okay, so the technology to do all of these things is very cheap now. So more and more of these are being used. A time-driven event where the controller executes the event either at a specific point in time or after a certain amount of time has lapsed. Examples, the factory shop clock sounds a bell at specific times to indicate start of shift, break start, and stops times, and the end of shift. Increasingly, they're actually putting a bell or buzzer sound every time tack time comes around. Heat treating operations must be carried out for a certain length of time. We have to get when we're heat treating, we have to get to the proper phase state of the material before it can be withdrawn. In a washing machine, the agitation cycle is set to operate for a certain length of time. Okay, but filling the tub in the washing machine is event-driven. So, two types of discrete control that can be used. One is logic controls. That controls the event-driven changes. So the output depends on the value of the input. So parameters and variables, you have a 0 or 1 condition, on or off. A sequence control, on the other hand, controls the execution of time-driven changes. So an internal timing device determines when to initiate changes in the output variables. So when we think about computer process control, the timeline, first of all, these guys say it started in the 50s. Actually, depending on how you define computer, it started much earlier. It was first used in the process industries. First, we had mainframe computers. They were very slow and expensive, and had a certain amount of unreliability. We had a set point control, direct digital control system started in 1962. Mini computers were first introduced in the late 1960s, and microcomputers introduced in the early 70s, right? So now we have we can drive things with very tiny integrated circuits that do the work that a lot of these computers, it took the entire computer to do. Now it's just a component in the machine. We had programmable logic controllers introduced in the 1970s for discrete process control. Distributed control starting around 1975. And PCs for process control in the early 1990s. Oh, they mean PC computers. I was overthinking it there. All right, so for real-time process control, we have two basic requirements. One is process-initiated interrupts. That's where the controller has to respond to incoming signals from the process. So those are our event-driven changes. And depending on the priority given to events, the controller may interrupt the current program to respond. Then we have the timer-initiated actions. The controller must be able to execute certain actions at specified points in time. Right, so those are our time-driven changes. One example is scanning sensor values, turning switches on and off, and recomputing the optimal parameter values. Other requirements that are needed for computer control, commands to process the process actuators. System and program initiated events. A system initiated event is a communication between the computer and the peripherals involved. Program initiated events, non-process related actions, such as printing out reports at intervals. We might also have operator-initiated events where we have input from our personnel, right? For example, we might have an emergency stop button. So, our computer controls are capable of polling, in other words, data sampling, interlocks that mean that you cannot open a certain part of the machine or interrupt a process while the control is on. An interrupt system to stop the system, and exception handling. What happens if the wrong part is on the line, or some other aspect where the controller can say, well, wait a minute, this isn't right, we're stopping the system. So polling, we're doing periodic sampling of our data so that we know the status of our process issues. Our polling frequency is going to be the reciprocal of the time interval between data samples. Our polling order is the order in which our data collection points are sampled, and our format, polling format, may be all sensors are polled every cycle, update only the data that has changed this cycle, and a high level or low level type of scanning. All right, so interlocks are safeguard mechanisms. So they are coordinating the activities of two or more devices and preventing one device, or it could be a person, from interfering with the others. So you have input interlocks, where a signal from an external device sent to the controller possibly says proceed to execute the work cycle program or to interrupt the execution of the work cycle program. And you have output interlocks where a signal is sent from the controller to an external device. The interrupt system, a computer control feature permitting the execution of the current program to be suspended in order to execute another program in response to an incoming signal indicating a higher priority event. So we can have an internal interrupt that is generated by the computer itself. So that might be a timer initiated event, polling, system and program initiated interrupts, or external interrupts. So they are generated external to the computer. So you might have process initiated interrupts or operator input into the interrupt. All right, so in this diagram, we see a single level interrupt system. Our interrupt mode is up here, and our normal mode down here. Task 1 arrives. When task 2 arrives, it waits until task 1 is done right here. Task 3 has arrived also in the meantime, but when task 1 is over, task 2 starts. Task 3 continues to wait until task 2 is done, and then task 3 is done, and we're back. Here we have here on the bottom we have a multi-level interrupt system. So we have our normal mode. Task 1 arrives. It is executed. Task 2 arrives. It interrupts task 1 and is being executed. when task 3 arrives, which interrupts task 2, task 3 has the highest priority, so it is completed, and then task 2 goes back to being completed, and then finally task 1 is able to be completed when both tasks 3 and 2 have been finished. All right, so exception handling. An exception is an event that is outside the normal or desired operation of the process control system. Okay, easy enough. So an example might be a product quality problem. Right now we have sensors that are very good. They can detect, oh wait, this hole wasn't drilled all the way through, or this shape is not right for this part. It might be a process variable outside our normal operating range. It might be a shortage of raw materials, a hazardous conditions. The example they give is fire. I'm hoping we don't have that many fires, but on the other hand, I once worked at a place where the cranes caught on fire all the time, which made for an exciting time because they were way up in the air. And it might be a controller malfunction. So our exception handling is a form of our error detection and recovery. All right, so our computer process control, first of all, it might just be process monitoring. In that case, the process is going on, the process variables are coming out, and the computer just records the data that is collected from the process variables as they come out. An open loop process control, we've talked about that before. The computer gives control commands to the process, and then the process variables go on. But again, the computer is just giving commands. It is not adjusting the process as it goes. In a closed loop process control, the computer gives control commands to the process. The process variables are measured, and then that is fed back to the computer. It may be just data collection, or it may be also the computer is correcting as we go. So our forms of computer process control can be computer process monitoring, direct digital control, or DDC, computer numeric control and robotics. We may have programmable logic controllers and equipment that is related to that. We may have supervisory control, and we're acquiring data at the same time. We may have a distributed control system. In other words, not all the control is vested in one computer. We might have personal computers in the process control. In other words, small computers are controlling aspects of our process. And there might be integration of our factory data across the whole enterprise. More and more, that eighth option is becoming popular. All right, so what happens when we have computer process monitor? The computer observes the process and the associated equipment, and it's collecting and recording data from the operation. In that case, the computer is not directly controlling the process. So it's collecting data, the process data, the input parameters and output variables, equipment data, the machine utilization, tool change scheduling, diagnosis of malfunctions, product data. Often that kind of quality control is to satisfy government requirements. Might be pharmaceutical processing, medical processing. This is also kind of important in process industries such as oil refining, right? The oil, when it's refined into gasoline, kerosene, diesel, all of these have specific parameters they have to fall within. All right, so in a direct digital control system, we have replaced parts of the system that would have been conventional analog control with digital computers, right? So in the 1960s, they were using mainframes for this. This was used in process industries. So they did it with a time-shared sample data basis rather than dedicated components, right? Typically, mainframes were so large and so expensive that one factory would have one computer and everything had to be run off of that. So it would do a microsecond's worth of attention to process one, then a microsecond's worth to process two, and so on. All right, so when we're talking analog control, we have our input parameters, our process, and our output variables. Our output variables mean that we have sensors, transducers that are measuring important output variables. They are sending it to a display instrument. We have a set point, a comparator that says, oops, that says, yes, these are the same, or no, they're not the same. It goes into an analog controller, then through an amplifier and an actuator to change the input variable that is going to affect the output variables that were measured. With a direct digital control system, we still have our input parameters, our process, our output variables. But we have many more sensors. We're sensing more variables. It goes into a multiplexer, then into an analog direct controller. We have an operator console and a direct digital control system. Those are communicating back and forth. Then it goes to a direct actuator control through a multiplexer, and actuators work on various input parameters. So, All right, so originally they thought this is gonna be more efficient than doing the same thing with analog controllers. But they figured out that, wait a minute, we can do more things with this than we could. For example, they combine discrete and continuous controls. You can integrate and optimize multiple loops, and we can edit those control programs more easily than we could adjust the old analog controllers. Our computer numeric control, well, I'll talk about robotics in a second. So the computer numerical control, the computer directs a machine tool through the processing steps, and that is defined by a program of instructions. So I would advise all engineers to learn to program CNC. There is a huge shortage of CNC programmers in America. A word to the wise. So one distinctive feature of numerical control is control of the position of the tool against the position of the object being processed. We often have to do computations to determine what is the tool trajectory. Although now we also have programs that will automatically program the tool trajectory for a given object. Industrial robotics, we have robots, they have manipulator joints, and they're controlled in a way that they move and orient the end of arm where the actuators are through a sequence of positions in the work site. Ooh, pardon me. Programmable logic controllers, or PLCs, they're microprocessor-based controllers executing programs of instructions to implement our logic, sequencing, counting, and arithmetic functions to control the industrial machines and processes, okay? They were introduced around 1970, replacing electromechanical relay controllers in discrete product manufacturing. Today, PLCs can perform both discrete and continuous control, and they're used in process industries and discrete product industries. Equipment that's related to PLCs are programmable automatic controllers, or PAC. So that's a digital controller combining the capabilities of a personal computer and those of a conventional PLC. So you have the input-output capabilities of a PLC, and that is combined with data processing, network connectivity, and enterprise data features of a PC. We can also have remote terminal units, or RTUs, where this is a microprocessor-based device. We connect to the process, receive signals from sensors, and convert them to the digital data to use by the central control computer. More and more circuits are taking on the characteristics that whole computers used to embody. Supervisory control, usually we associate that with process industries where supervisory control has a control system that manages the activities of integrated unit operations to achieve certain economic objectives, like making money. In discrete manufacturing, our supervisory control is the control system directing and coordinating the activities of interacting pieces of equipment in a manufacturing system. So it may be doing the function of scheduling the production, tracking tool lives, optimizing operating parameters. Pardon me. Our supervisory control superimposed on a process level control system. All right, so once again, we have our input parameters, we have our process, we have our output variables, right? The output variables we want to line up with our economic objectives. We get feedback from our output variables that goes into our direct process controller. The supervisory control is monitoring the direct process controller and interfaces with the humans in the system so that they can give input that the digital components may not be able to. And then we have actuators for the input parameters. All right, so our supervisory control and data acquisition, or SCADA, in this case, we're saying our supervisory control system also has to collect data from the process. So the system consists of central supervisory control computer system, a human-machine interface, or HMI, distributed PLCs and RTUs connected to the process, and communications networks, a network that connects the central computer with those remote programmable logic controllers and the remote terminal units. A distributed control system, we have multiple microcomputers that are connected. They share and distribute the process control workload. So you have multiple process control stations that control individual loops and devices. A central control room where the supervisory control is accomplished. Local operators stations for redundancy. And a communications network that ties everything together. All right, so in this case, we're seeing we have our communications network, we have local operator stations, a central control room, and then we have process stations that are performing various processes on uh, on the main process, so that we go from raw material to product. A distributed control system, first of all, we can have a very basic configuration that can be expanded and enhanced over time. Multiple computers can facilitate the parallel multitasking. We have redundancy due to multiple computers. We may have much more computing power in each computer than is needed, so that if a computer goes down, other computers can take up that load. The control cabling is a smaller amount than a central controller configuration. And our networking gives us process information all the way through the enterprise for more efficiency in our plant and process management. So, the difference between a distributed control system and a SCADA system may just be a matter of our terminology. When we say a distributed system, we're emphasizing our interconnected computers. Our supervisory control emphasizes the use of a central computer that manages that interconnected collection of remote controller and our data acquisition devices. So when we use personal computers in process control, first of all, it might be used for an operator interface. Our PC is interfaced to one or more programmable logic controllers or any other devices, and they directly control the process. So our PC then is performing monitoring and supervisory function, but it doesn't directly control the process. In a direct control system, our PC is interfaced directly to the process and controls the operations in real time. Now, they're saying traditional thinking is that this is risky, but less complexity usually leads to lower risk. So using personal computers for direct control, well, first of all, almost everyone is familiar with personal computers these days. It's not mysterious like when the first personal computers came out and you had to acquire a lot of knowledge to be able to use them. Now we turn our children loose on them. We have easy availability of high performance personal computers. And in fact, the speeds of personal computers are faster than programmable logic controllers. We've gone to an open architecture philosophy with our personal computers, and so all the hardware and software complies with standards that let their products be interconnected to the same control system. And for those of us that remember the days when you bought software, it had to be particularly for your specific computer, this is a happy day. Personal computer operating systems can facilitate that real-time control and networking. And we also have personal computers that are not as delicate as the first ones and can be used in industrial environments. So, one of the things that we aim for is integration of all of our data across the whole enterprise. So we can use personal computers to build a distributed control and get that integration of factory operations data. Right? So instead of being several hours or even several days behind time integrating our data, we're getting it right now and we're able to see how everything is working. This works well with our worker empowerment philosophy that is a different philosophy than the 20th century or 19th century management philosophies. And it means we can have fewer levels of company management, which is also consistent with our 21st century management philosophy. So, we often use the term Enterprise Resource Planning, or ERP, to refer to a software system where we get a company-wide integration, not only of the factory data, but all the data that we need for our business functions in the organization. All right, so when we have that enterprise-wide integration of our factory data, we can have managers having direct access to the factory operations. The planners always have the most current data on our production times and rates and can do better scheduling. Our sales personnel can give better delivery dates to customers based on the amount of loading in our factory. Our order trackers can give current status information to our customers. Our quality control can access the quality issues from previous orders. Accounting has our recent cost data. Production personnel can access the product design data in case there's any question or ambiguity about what should be done. All right, so here you can see we end up with a 4-level process. Here at the bottom we have our process itself. We have process stations. On top of that is local operator stations and our central control room. All of these are feeding data upward into the engineering workstation, finance, production planning, purchasing, and quality control. Again, the advantage of this is we know on a minute-by-minute, second-by-second basis what's happening. Don't forget that this material is copyrighted. And we have this little graphic here in case you were thinking of forgetting. Are there any questions on our Chapter 5 Industrial Control Systems? Okay, well, we still have about 20 minutes, so let's plunge boldly into Chapter 6. All right, so Chapter 6 is hardware components for automation. So we're going to talk about sensors, actuators, analog digital conversions, input-output devices for discrete data. All right, so first of all, we have to have a computer to process interface. Our computer has to collect data from the process and transmit signals to the production process. So the components we require for that are sensors. They might measure continuous or discrete process variables. We have to have actuators that are able to raise or lower the continuous and discrete process parameters. Devices for analog to digital conversion and digital to analog conversion. And input-output devices for discrete data collection. All right, so here we have a process. It's got the equipment inside there. We have continuous parameters and discrete parameters coming in. And then on the output, we have continuous variables and discrete variables. So the discrete variables are measured by discrete sensors, goes to the control computer. The control computer has discrete actuators that then control the discrete parameters. The continuous variables also have sensors that are analog sensors. They go to an analog digital converter into the control computer. Output from the control computer goes to a digital analog converter. We have analog actuators, and that goes to the continuous parameters. Right, now I'm sure you already understand so well why for continuous variables we need to use analog aspects, where for discrete we can just stick with straight digital. So no reason to go into that at all. No, I'm lying. We have to use analog in continuous parameters and continuous variables because we do things like we want to close the valve a skosh as opposed to a discrete parameter where we say, okay, well, you can only close the valve by one step, right? You can't go half a step with a discrete or a digital device. All right. A sensor is a transducer that converts a physical stimulus from one form into a more useful form to measure the stimulus. Boy, that is a high-level explanation of that. So in other words, a sensor might be a physical switch that when something is on top of it, it registers that it's on, and then when that something is gone, it registers off. It could be a light beam that gets interrupted. It might be measuring magnetism from something going over. There's some way of detecting that physical stimulus. So if they're analog, there's a continuous analog signal. If it's discrete, it gives us outputs that only have certain values, right? And by now, I'm sure you're aware of the difference between continuous and discrete values. The discrete sensors may be binary, where it's either 0 or 1. It's either off or it's on. Or it might be digital in that it is counting something. So, our sensor transfer function the mathematical relationship between the value of our stimulus and the value of the signal produced by the sensor, we're saying is uppercase S equals the function of lowercase s, where S, uppercase S is the output signal, lowercase s is the stimulus, and f of s is the functional relationship between them. Hopefully, our ideal functional form is just a proportional relationship. S equals C plus MS. If we have binary sensors, then our uppercase S equals 1 if lowercase s is just greater than 0. And uppercase S equals 0 if our lowercase s, our stimulus, is less than or equal to 0. All right, so we have actuators. These are hardware where we convert a control command into a change in some parameter. Usually this is mechanical, right? So it might be position, it might be velocity. An actuator is a transducer because we're changing a physical quantity into an alternative form. So an actuator is usually activated by a low-level command signal, so an amplifier may be required to provide sufficient power to drive the actuator. All right, so we can have different types of actuators. We can have electric, where we have electric motors, solenoids, or electromechanical relays. can be hydraulic, where we use hydraulic fluid to amplify the controller command signal, or pneumatic, which uses the same idea, where we use compressed air as our force. All right, so electric motors, we can have DC motors, in other words, direct current, and the common type is the DC servo motor. With alternating current motors, we can have synchronous motors or induction motors. Then we can also have stepper motors, where the motor only moves by certain values, and linear motors. All right, so a typical configuration for a rotating electric motor, we have the housing, we have a mounting plate, and a motor shaft. We have a powered cable where the electricity comes in. We have the rotor field and the stator field, which make the motor go. So the idea is that the axis of the stator field causes the axis of the rotor field to move, bringing about changing the electrical energy into rotational energy. Yeah. You know what? It's a little early. Let me stop here. My voice is just about gone. And we will pick up with slide 11 in our next exciting episode. Oh, I'm sorry I did that. All right, and maybe we should start all the way back here at, okay, are there any questions about today's exciting class? Hearing none, I am then going to declare the class is over. Have fun. I'll see you next Wednesday. We don't have class on Monday. Are you okay, Marcy?
Yeah.
Okay. Thank God for that. Oh, right. That's not it. Oh. Stop sharing. Leave the meeting, really leave the meeting. Oh, okay. You know, it's kind of nice not to have very many teachers using the computer, because I can leave a lot of stuff up and no one bothers it. And